Today I'm going to try to talk about something I've been working on relatively recently, which is the algorithmic information theory. So I have been working on machine learning and dynamical systems for a while now, and then I'm trying to add a third component, which is algorithmic information theory. So that's mostly through discussions with Marcus Hütter from DeepMind. So he's someone who believes that AIT is the key to AGI, but okay, I don't understand totally AGI, but I thought it may be interesting to update his arguments to dynamical systems. And so, yeah, so this is, as I said, this is more of an attempt, so I'll be interested in hearing your feedback about this kind of framework. So, okay, yeah, so the general context is how to analyze complex systems, and I think all of us here are interested in complex systems. So among the current approaches to analyze complex systems are algorithmic information theory that was developed by Kolmogorov, Solomonov, and Shaitin in the 60s. So it allows to characterize concepts like complexity. Okay, what is complexity? What is simplicity, randomness, induction, and information contact, for example. But it's currently hard to compute the quantities that appear in the theory. So this theory, I mean, the key concept there is Kolmogorov complexity and different variants around the Kolmogorov complexity, but it's not something that one can compute. Yeah, so this leads to other approaches in general, which are like machine learning that we are all familiar with. So it's concerned with the algorithm designed to accomplish a certain task whose performance improves with the input of more data. So it allows the analysis of some very high dimensional complex systems on the basis of data when the model is not even known. But yeah, but there is no theory of machine learning. So its theoretical foundations are quite limited. And it's not clear why the algorithms in machine learning work and what is their domain of applicability. So we also have another approach of analyzing complex systems is the theory of dynamical systems. So that allows to analyze complex systems when the model is known. So it has been mostly formalized by Poincaré and Lyapunov in the late 1800s. So it offers non-trivial ways to analyze dynamical systems. So it has the status of theory, but it is currently limited to low-dimensional models. So from here, if we look at this present, like the way we are introducing this thing, I mean, it makes sense to combine between the three. And so we have like a machine learning that is like quite popular nowadays, but it lacks a theoretical foundation. It would make sense to strengthen it with existing theories, which are the theory of dynamical systems and algorithmic information theory. So my talk will be mainly concerned with the direction of machine learning and dynamical systems and machine learning and IIT. So I worked a little bit on the dynamical system and IIT, but it's not the object of today's talk. So for MLDS, machine learning and dynamical systems, so the goal is to fill the gap between machine learning and dynamical systems in the following directions. So machine learning for dynamical systems, where the goal is to analyze dynamical systems on the basis of observed data rather than attempt to study them analytically. So this would allow to extend the boundaries of the classical theory of dynamical systems. Other direction is dynamical systems for machine learning, where here we want to look at algorithms of machine learning as dynamical systems, where the time is the time on the computer and not necessarily on the clock. So here, this would give solid foundations to existing methods and understand their true potential and limits, and ideally identify the domain of applicability of the algorithm in machine learning. Machine learning and AIT. So here we are interested in bridging the gap between machine learning and algorithmic information theory. Machine learning for AIT. So here we want to look at applications of Solomonov induction, algorithmic probability, and links between information learning and data compression. So in a way, AIT can be viewed as generalized version of Bayesian statistics, where we have a universal prior that is given by the Solomonov prior, which is sometimes used called the universal prior. So here we would be interested in seeing how machine learning can be adapted accordingly, and then how we can use machine learning to compute quantities that appear in the theory of algorithmic information, and precisely seeing how we can compute Kolmogorov complexity and its variance. Other direction is algorithmic information for theory for machine learning. So here we want to, again, the key is to strengthen the theoretical foundation of machine learning. So currently, I mean, many of the approaches are based on statistics, but some argue that one of the weaknesses of the theoretical foundations of machine learning are due to the overemphasis on statistics. So it would be nice to look at all the theoretical frameworks. So here we would like to argue for an AIT for machine learning. So here we want to see, for example, why certain methods in machine learning will a priori work. So here the key is a priori work or a priori will not work, because we are going to a little bit deeper in the way algorithms work, and then we want to see if there is something that can be said about the structure of the data and the structure of the algorithm together, and see whether they are going to work as a whole or will not work as a whole. Again, here it's not only about looking at models, but also about looking at models plus data. And this is, for example, that we'll talk about in the principle of the minimum description length. Yeah, so this is, I think I talked a lot about this. So I started my journey in machine learning around 2008 through the motivation by Steve Smale, I mean, who about like in 2007 said that the unification of dynamical system and machine learning is a major problem. And so, yeah, so this, for example, what we wrote in 2012, that it's easier to simulate dynamical systems, but mathematical theory at that time was still underdeveloped. This like machine learning and dynamical systems. AIT and dynamical systems. So here we are proposing to adopt a probability complexity perspective in analyzing dynamical systems in view of enriching and strengthening statistical learning theories related to prediction and analysis, especially of systems where there is a lot of uncertainty and stochasticity. But as I said, I mean, this is not, I will not talk about the direction AIT and dynamical systems. And the other direction that I'll be covering today is AIT and machine learning. So here the goal is to reformulate algorithms in machine learning using tools from AIT with the aim of giving them a more solid theoretical foundation. So we got already two papers on this. One of them is something that got accepted recently. So I'm going to talk a little bit about this work. Yeah, so the talk is essentially probably going to be made of, so I don't have 3 parts, but I don't think I'll be able to cover everything. So I'll try to cover the first and second part. Third part is about Kohlhoff and Poincare normal form. So Zhongshan will talk about them in his poster. So I'll just cover the AIT perspective on what he's going to present in the posters. Yeah, so kernel methods, so they appeared in the 30s. They are quite old. As an answer to the question, when is it possible to embed a metric space into a Hilbert space? And so, the answer at that time was that if the metric satisfies certain conditions, it is possible to embed the metric space into a special kind of Hilbert spaces that are called RKHS. Motivation at that time was that people had complex problems, but they didn't have the computational power. So the idea was to work on different spaces, like Hilbert spaces, which are linear spaces, where computations become simpler. So properties of RKHS have been further studied in the 50s, especially through work of Aonjan, Schwartz, and then they died a little bit, and then they were resurrected through Wahba and in the 90s, and then Smale, and then I think since the work of Smale in the early 2000s, they have been quite popular. So most recently, there is like a bridging the gap between kernel method and neural networks. Yeah, so there are, before anything else, there are Hilbert spaces with 2 extra properties, which is the reproducing property and this ability to that the reproducing kernel spans the whole space of function we are dealing with. So we have this following properties. I'll go quickly over kernel method. I'm assuming that a lot of people now got kernel methods. So we have popular ones are monomial, Gaussian kernel, and hyperbolic tangent. So they play an important role in learning theory, where the goal is to approximate random functions, approximate unknown functions from random samples. So we have we have a functional that is to be minimized. So we know the closed expression when we minimize this functional, but since we don't know a lot of things in this functional, we end up regularizing and approximating the error functional. But this leads to a closed form expression of the approximation. So here it's like linear in the feature maps in the VJX, and the CJs themselves, they satisfy a system of linear equations. So that's the advantage of RKHS. Then the natural question is how to learn kernels. So that's, yeah, so there have been like work on kernel flows, which is like a method of learning kernels, and then that we extended to learning dynamical systems with different variants. And yeah, so the goal is to reformulate this method using AIT. So kernel flows is based on the following. So we just come back to the regular problem of recovering an unknown function from random samples. So this problem is ill-posed in general, but it becomes well-posed if one works in a certain Banach space with the following norms. And so it's based on the premise that a kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. So this is, for example, this definition is what led me to start thinking about kernel complexity and AIT and compression, because here it's saying that the kernel is good if we don't have significant loss in performance if we reduce the number of data. So this leads to to the idea of compression. And in a way, what kernel complexity is saying is just telling you that we are trying to compress, and it's formalizing the idea of compression. So that's somehow, this is how I started thinking about the whole reformulation of kernel methods using kernel complexities, exactly through this point of view that a kernel is good if you are able to compress the number of data that you are using without losing performance. So this, for example, led to the introduction of the following relative error, where one is based on the full data set, so the V star, and the VS is based on like half of the data points. But again, half is just something generic that essentially means compression. So the way it works is that if you have a kernel that is parameterized by theta, the kernel flows algorithm goes as follows. First, start by having a random sample, and then XB, and then of size capital N, and then a random subsample of size capital N over 2. But again, this has to be viewed as a compressed version of the original data set. Compute the relative error, and then update the parameters in the direction of the gradient descent of direction of rho. So you just get theta k plus 1 is equal to theta k minus delta gradient of rho with respect to theta. So now we extended this to the case of dynamics, where we have time series, and we want to forecast xn plus 1 modulo the knowledge of x1 to xn. I mean, that's only one of the objectives, because in dynamical systems, we are not only interested in forecasting, we are also interested in dynamical properties. And so here, given the previous, we can learn the right-hand side of the dynamical system using the representative theorem. But then, as I said, since in dynamics, it's not only about short-term predictions, it's also about other dynamical properties. So these are two other metrics. First one is for short-term predictions. Then you have one that is related to Lyapunov exponents. And our goal is to learn the kernel in such a way that the Lyapunov exponents of the learned system and the true system are close to each other. So here we say that the kernel is good if the approximation of the maximal Lyapunov exponent doesn't change much when we halve the number of data points. But we can also take into account other Lyapunov exponents, not only the maximal one, but we can also use other metrics that are indicative in dynamics. So this is, in a way, this is like about long-term behavior. So MMD, this is about statistical behavior. So because in dynamics, again, we have a long-term, we can also have like a short-term, we also have statistical behavior. So this is what the MMD is, metric is doing, is that if we take the maximum indiscrepancy between two subsamples, then we say that the kernel is good if the MMD between two subsamples is small. So MMD is, in a way, is generalization of the difference between the means in the RKHS. And then we have also, when we are dealing with attractors, this is more of a geometric in a way. We say that the kernel is good if the Hausdorff distance between the construction of the attractor with the capital N points versus N over 2 doesn't change much. But you see, the common point between all these metrics is the ability to compress. So it's always about compression and using less data, and then and capturing essential properties of the dynamics via data. So here, I'm just going to illustrate this how we proceed in practice. So if we take a large kernel of large dictionary of kernels that are denoted by k little I with m kernels, so we modify one of the metrics. So this is can be changed, as I said, and then we just add L1 penalty. And so, yeah, just to 0 maximum number of coefficients here. And yeah, so we apply to the database of 131 chaotic dynamical systems, so that we use this kernel with 40 parameters. In a way, kernel flows can be also viewed as a way of like training, like a trainable machine learning method that is not a neural network. So here we are just using 40 parameters. So you see, we don't really need to think about the architecture of the neural network. And so we just have a sum of kernels, 15 kernels with 40 parameters. And so we apply this to like this database of 133 systems. This, for example, for this system. So this is like regular kernel flows versus sparse kernel flows. This is like another system. So as I said, this entire data set. And we see that we are able to minimize this map, which is like short-term prediction for these two systems. This is for regular kernel flows. This is for sparse kernel flows, and also long-term when we are learning the attractors. So yeah, so now I move to part 2, which is the link between AIT and the kernel methods. When I talk about, usually when I say AIT and machine learning, I really mean AIT and kernel methods. So here I also divided it into AIT for kernel methods and kernel method for AIT. So just a short introduction to AIT. So what is AIT? So it's a field within computer science that is directly connects computation, computability theory, and information theory. And so here, in a way, we want to mimic what Mackay said in his book on information theory, that machine learning and information theory are two sides of the same coin. So we want to say that also ML, machine learning and AIT are two sides of the same coin, and that, in a way, this is like the goal of this the research direction of connecting ML and AIT. So central quantity of AIT is Kolmogorov complexity, which measures the complexity of an individual object as the amount of information required to describe or generate X. So technically, is the length of the shortest program that produces X when given an input as an input to a universal Turing machine. So here, this is not really important. The key is really to think about the length of the shortest program that generates the data. For example, we see that if X contains repeating patterns like 1 0 1 0 10 times, then it's easy to compress, and then the program will be just like to print 1 0 10 times. And so if so in that case, the Kolmogorov complexity will be small. So on the other hand, if we have randomly generated string of data of length n, then it's unlikely to contain any significant pattern. And so it's unlikely that we can write a simple code that generates the data. And therefore, the Kolmogorov complexity will be approximately equal to n bits, so if we are dealing with n bits. So that's, in a way, we are seeing that at the very moment we have data and patterns, then we can compress, and so Kolmogorov complexity will be smaller. And so one could also think about dynamics. Right? If you have a dynamical system, then there is like an underlying equation that is generating the data, or there are like underlying structures or patterns that are generating this kind of patterns. And so we expect that the Kolmogorov complexity in that sense is smaller when we are dealing with dynamics. I mean, that's in a way the main concept that we are using when we are bridging between AIT and dynamical systems. It's based on the fact that dynamical systems are not totally void of patterns. I mean, there's something going on when we have dynamical system, and so this leads to a lower complexity compared to something that is that has no equations, that is totally random, or that is not that has no patterns. Yeah. So now the link between kernel complexity and reproducing kernel is natural and seems intuitive. So kernels, what are they? They are a measure of similarity, and so it makes sense to say that if two objects are similar, then they can be compressed one to the other, and if they are not similar, then they cannot be compressed. So so in that case, we could say that reasonable definition for the similarity between two objects is how difficult it is to transform them into each other. And this is exactly the definition of the conditional kernel complexity. That is the length of the shortest program that computes x from y, which is kx given y. So essentially, it's the length of the shortest program to output x given y as extra input. So if y is n-informative or n-related to x, then kx given y will be essentially the same as k of x. However, if y contains a lot of information relevant to x, then kx given y will be significantly smaller. And so this leads to introducing some complexity, kernel complexity-based kernels. Here I'm going to talk about two kernels. But in the paper, we have a few other ones that are based on other concepts in AIT. So the first one is the conditional kernel complexity-based kernel. So it's based on symmetrizing the conditional kernel complexity and plus adding a certain constant to make it. So all of this is just to make sure that the resulting kernel is a proper reproducing kernel. So we define the conditional kernel of complexity-based kernel as the exponential of minus lambda of dk, which is the metric that we are defining above. So this kernel provides a measure of similarity between x and y, where smaller values of k sim, which is a symmetrized version of the conditional kernel complexity, correspond to greater similarity, and larger values indicate dissimilarity. The other kernel is the symmetrized algorithmic mutual information kernel that is defined as, that is related to something called the algorithmic mutual information, which is essentially the gap between the standard kernel complexity and the conditional kernel complexity. So if you remember the way I introduced the link between kernel complexity and kernel method. So here we said that if y is n-informative or n-related to x, then kx given y will be essentially the same as kx, which means that the gap between the two can be used to build the kernel, which is exactly what is done here, that kx minus kx given y. And then we symmetrize because we want the reproducing kernel to be symmetric. And then we add an extra constant just to make sure that the resulting kernel is positive semi-definite. So yeah, if y contains significant information about x, then kx given y will be much smaller than k of x, so leading to higher mutual information. And so if we take the max, then we select the direction that provides the most information for kernel construction. And so this approach, ensures that the kernel captures the strongest informational relationship between x and y, and so emphasizing on the effectiveness of the similarity measure. So then we have natural question that will come now, which is how universal are these kernels? So can we prove that the kernels, kernel complexity-based kernels, are universal kernels? This is something that we just started thinking about recently. Other question is how to compute them. So luckily, there is a way to compute them. They are not totally abstract objects. So people have been thinking about approximating kernel complexity using compressors like Lempel-Ziff. And even Marcus Huder, he has an award to build better compressors. And so now, to estimate the conditional kernel complexity, we use this identity. The conditional kernel complexity can be approximated by mutual kernel complexity minus kx and versus concatenation of the string. So essentially, what we are going to end up doing in practice is just to take the concatenation of x and y as a longer string, and then compute the kernel complexity, and then subtract from it kx to get conditional kernel complexity. And but on its own, I mean, computing conditional kernel complexity is still like a research direction on its own, so that we leave for future work. But you see here the fact that we are making the link with machine learning and kernel methods is also opening new directions in AIT itself. And yeah, so now we want to reformulate sparse kernel flows from an AIT point of view. So we are going to do this via the minimum description length principle. So which is like a generalization of Occam's razor. So this principle provides a criterion for the selection of models regardless of their complexity, without the restrictive assumption that the data from a sample come from truth distribution. It can be viewed as a downscaled practical version of Kolmogorov complexity. And it states that among all competing models, the one that allows to compress the data plus the model most is the one that should be taken into account, and that would lead to better generalization. Because by compressing, in the sense using Kolmogorov complexity to compress both data and model, then we are able to detect patterns and regularity, and hence the better the prediction will be. And again, it just says to select the simplest model that is consistent with the data, and simplest means lower Kolmogorov complexity. Yeah, so it's the addition of the code of the code length for the model, which separates it from the familiar maximum likelihood principle and makes it more general in that sense. So how does it work? So if we have a set M of countable class of models, theories, hypotheses, probabilities over sequences, etc. So they are sorted out with respect to their complexity, kernel complexity. And so here we assume that we are encompassing the M noun true sampling distribution P, but again, M can be anything, so it's easy to include this. So so here the goal is to select Q in M that leads to the shortest code on the observed data. And so this leads to the description length, which is like minus log of Q of X plus K of Q, which is the kernel complexity of the model. And the idea is to minimize this over M. So this is why it's called the minimum description length. And so MDL selects the following as the minimizer. So we take the argument of minus log Q plus K of Q. So yeah, so here we can always easily make a link with Bayesian prediction by just taking into account a weighted sum of the Qs. But again, here we are just making links, but it doesn't mean that they are not. No, there are links, but this doesn't mean that it's exactly the same thing. And so here we want just to show the link between, or actually compare between MDL as a principle versus regularization machine learning. So in MDL, the loss has to be log loss, while the penalization term can be anything. It is related directly to Kolmogorov complexity. In machine learning, the loss can be anything, but the regularization is fine-tuned via parameter lambda. So there's always this cross-validation that is done in general to find the right parameter. But there's definitely a link, as we are going to see here, that method of sparse kernel flows is just an abstract version of model selection using MDL. So the differences between and commonalities between MDL and regularization machine learning are as follows. So the MDL principle is completely general. So it makes no assumption on the underlying model class, no IID or stationarity or organicity or parametric or smoothness assumptions, while regularization machine learning is somewhat tailored towards IID data. MDL is limited to log loss, while any loss can be used in regularization machine learning. And regularization machine learning requires choosing a penalty R and tuning its strength, often by cross-validation, while MDL theory dictates the penalty term. So that's the link somehow that I was talking about. So if we approach sparse kernel flows from the point of view of MDL, as I said, I mean, here, this is just a term that you can replace with whatever metric you like. But essentially, MDL says that the penalty, the regularizer has to have the form P over 2 log n, where P is the number of non-zero parameters. And this is where sparse kernel flows come in, because it's zeroing the maximum number of parameters. So P being the number of non-zero parameters, P over 2 log n is the MDL regularization term. And so because of this, I mean, one would have to solve 2 to the power m optimization problems, but usually this is quite complex. And so we approximate this by the L1 penalty term that we got in sparse kernel flows. So essentially, what sparse kernel flows is really just a surrogate loss, which is like an L1 approximation of the MDL principle. And so sparse kernel flows is the natural way to learn kernels from data. And so there is no need to use cross-validation to justify its efficiency, and everything follows from AIT. So the fact that sparse kernel flows considers that a kernel is good if the number of points can be halved without loss in performance, which is like compression of data, plus reduce the number of parameters, so which is like reducing the complexity of the number of parameters via sparsification, is consistent, makes it consistent with AIT and the MDL principle. And here we conjecture that the minimal number of points that are needed for here, like for the MDL principle, are the covering numbers, and that this would be giving the lowest Kolmogorov complexity, but that's still like an open question. Okay, now we want to move to extending MDL, and we are going to show how AIT can offer tools to learn kernels in kernel density estimation. So far we have, as I said, we have been looking at AIT for kernel methods, and we want to see how, so sparse kernel flows is essentially supervised problem, because we have labels. So we are trying to approximate an unknown function from random samples, whether this is like a static function or dynamical system. So here I want to see how this AIT principle can lead to introducing ways to learn kernels in kernel density estimation, which is not a supervised problem. So it's like an unsupervised problem. So this is this is like a new method, but it will be interesting. So we applied it only to simple toy models. It will be interesting to see how this can be used in the context of dynamical systems, where we have mostly distribution, where it's not easy to define trajectories, like a context of random dynamics. So okay, so the MDL in reality handles only parametric models, where the parameter dimension D does not grow with little m, the number of data. But when we are dealing with non-parametric approaches that can store all data points or let the parameter count scale with n, then MDL actually doesn't properly work. And the classical example in kernel methods is the kernel density estimation, KDE, in which each sample xi acts as a center, so effectively making the model depend on the entire data set. And KDE, so here the estimator is it's a center on all the observables. So it's giving you that the estimate is 1 over n times the sum of k theta x xj, where xj are the observable. So the loss rank principle generalizes the minimal description length to more flexible models and arbitrary loss functions. So here we don't necessarily have the restriction of log form of the criterion. So for a data set X and the model parameter theta, the low rank principle defines a rank for X by counting how many hypothetical data sets X prime achieve a loss that is less or equal than the loss corresponding to the data set that we are observing. So if one takes the negative log of this rank, so this will lead to the definition of code length that is instrumental in AIT. So extending the MDL idea of describing X with respect to theta. And so this is exactly what leads to the ability to learn kernels, parameters of kernels in kernel density estimation. So here we proceed as follows. So we have choose a kernel function, k theta x prime. Now assume that you have a data set for which the KDE is to be learned. So we have the estimate, as we mentioned earlier, which is given by the average of k theta z xi. So here the estimate depends on the kernel parameter x theta. So we define the loss function as the negative log likelihood of the observed data set under the KDE model, which is like the minus the sum of log p hat theta x xi. And so the loss measures how well the kernel with parameters theta describes the data set x. And then in order to generate the hypothetical data set, so we just generate them here. The way we did it in practice, just to take uniformly generating random samples x prime. So this one serve as alternatives for evaluating how typical the observed data set x is under the kernel defined by theta. Then we compute the rank. So the rank is defined as the cardinality of the number of points x prime in the hypothetical data set, which is the alternative data set, such that the loss of theta with respect to x prime is less or equal than the loss of theta given x. So this rank quantifies how many hypothetical data sets x prime achieve a loss smaller than or equal to the loss of x. And so a higher rank indicates that x is more typical under theta. And so we convert this code length to convert the rank to code length. And this is just done by taking the log. And this, in a way, this is why the log is more general than MDL, because you can always play that trick of just taking the log is okay. And so this code length measures the description length of x under the kernel defined by theta. And smaller code lengths indicate kernels that are both descriptive of x and also allowed to generalize to alternative data sets x prime. So again, we are trying to go a little bit beyond the observable x and then take into account the ability of generalizing into hypothetical data sets, in which in our case is just uniform distribution. And to find the optimal kernel parameters, we just minimize the code length. So basically theta star will be the argmin of the code length of theta given x. And so this optimization ensures that the selected kernel parameters balance the trade-off between fitting the observed data set and generalizing to plausible alternative data sets. So here, just as I said, I just tried alternative data sets as coming from uniform distribution, but yeah, while preparing the talk, I thought, okay, maybe there's probably a better way of doing it, but maybe taking other probably distribution at the same time, or doing it for one and then using different other distributions. But I'm still not clear about this. But as I said in the example, I just use uniform to generate x prime. So what we did here is so we just we try to learn the parameters of the sum of two kernels. Here we wanted to learn the parameters of the coefficients and the parameters of the Gaussian kernel and the Ipanin-Shnikov kernel. So I have trouble saying it. And so so the full KDE for our data set is the following estimate. And as I said, so the unknown parameters are sigma h alpha and alpha Gauss and alpha Ipan. So first we compute the negative log likelihood. So this penalizes KDEs that fully fit the data. And then we, for each candidate parameter set, so we compute the rank. And we generate also the hypothetical data sets using uniform distribution. And then the rank is the cardinality of this set, the number of points, hypothetical data points, such that we have the negative log likelihood for the hypothetical data points is less than the observed one. And then we take the code length as the log of the rank plus epsilon, because just to regularize this code length. And then we did just simple grid search because we had only 4 parameters, but I'm sure that other frameworks can be used like JAX or other stuff. And yeah, so this, for example, what happened here. So we have, this is the data histogram. KDE before learning is the orange, and green is KDE after. I'm sure that this stuff can be improved a lot, but for me, it was just a proof of concept. And we see that things are working here. Yeah, okay, so I'm just going to go very quickly now over the second last part. So we want to go to show that it's possible to simplify PDEs using canon methods. And also it's possible to simplify ODEs using canon methods by tackling call-hop transformation, where we transform nonlinear PDEs to a linear PDE, and also Poincaré, where we try to remove the maximum number of terms in the Taylor series expansion of the Poincaré normal forms. But there are other formulations of normal forms that we are working on. But here, this work, I'm just focused on these 2 methods. So I said here, Zhongchen has 2 posters on this stuff, so we can go over the details. But the idea is to use canons. So to use canons to simplify the PDE. So we have, for example, Berger's equation. We have the heat equation, and we want to learn mappings that transform Berger's to heat using canon methods. So the approach here will be totally database. So it's database discovery of call-off, and ultimately we want to see if we can simplify a lot of nonlinear PDEs by canon methods. Yeah, so these are, for example, the results for call-off. So we have a copy of the heat equation, and then this is transformation without learning and also learning the canon. And so here, the problem of simplifying PDEs using canon methods is consistent with the MDL principle, since we are using the simplest model, because again, we are targeting a linear system. So again, simplification is there. So here we argue, so it still needs to be proven, but the argument here is that by simplifying, so the Kolmogorov complexity of the heat equation will be smaller than the Berger's equation. And so we have simplification and models. And then also, since we are compressing the number of data using sparse canal flows, then we are consistent with the MDL principle. Poincaré normal forms, so we have nonlinear ODE. So the idea is we Taylor expand F, and we want to get rid of the maximum number of terms using transformations. And the idea is to try to solve the homological equation that defines the normal form using canon methods, and also to discover the invariant terms. So yeah, as we said, we are going to focus on the indirect approach. So the direct approach that gives us the normal form directly by using the PDEs is like object of current work. So I'm not going to talk about it. And so the idea here is we want to learn the Poincaré normal forms directly from data. And so, for example, this is what happens with the Hopf bifurcation. So we take the example of the bristolator. We learn the normal form directly from data. And yeah, true normal form versus learned normal form. And also recover the limit cycle, true versus approximation, and the true radius from the theory of from a Hopf bifurcation theorem. And yeah, same here for like the time evolution of the coordinates, and yeah, the limit cycle. And yeah, same here again. We want to prove. So we argue that this is also consistent with the AIT. With MDL in particular, where we are compressing both data and models. Yeah, okay, so to conclude, so we introduced the method of sparse canal flows, and that it is efficient in learning a large database of chaotic systems. So then we reformulated the problem of learning canons from data using the MDL principle. So we show that the loss involved in the method of sparse canal flows can be viewed as a problem of data compression, and that the problem of learning canons from data using canal flows can be viewed as a problem of choosing the shortest description where the MDL principle can be applied. So this is said here in the context of supervised learning. So this point of view allowed to prove that learning canons from data using kernel flows, and in particular using sparse kernel flows, is the natural approach to adopt and is consistent with Occam's razor in its MDL version. So we also introduced KC-based, Kolmogorov complexity-based kernels, and they also showed that they offer tools to learn kernels in the context of unsupervised learning, but by using a generalization of the MDL principle, that is the lost rank principle, where it can be applied. And so all this work in a way shows that it is not necessary to use cross-validation to justify the efficiency of kernel flows and other kernel methods, probably. I mean, that's also another part of the project. So thereby illustrating that we do not have to go the statistical route, and you can directly work with code length and complexity, and so allowing for better theoretical foundation for machine learning methods. So we also argued that simplifying and linearizing ODEs and PDEs through Poincare normal flows is consistent with AIT, and our goal is to reformulate other machine learning and machine learning dynamical systems problems from an AIT point of view, in view of giving them a more solid foundation. Yeah, okay, thank you. Yeah.
Hi, good morning. So I'm Masaaki Imaizumi from the University of Tokyo, and also I have joined this RIKEN AP Center. So yeah, this title is somewhat like a very general. So I thought that I would like to present some like a more learning theory stuff, but I thought that this workshop learning dynamics, dynamical systems, and so I tried to like change my title and some other things. And so I'm basically a statistician and machine learner, and I'm not really expert with the dynamical systems, but I recently I'm really interested in like some like physics-based dynamic analysis, and I try to introduce like some kind of like a sub connection between like machine learning and dynamics or analysis. Okay. So and this is really like a fancy introduction. I mean, no information here. Like yeah, all of you may know that the recent success of the like modern data science technologies, including AI or deep learning or transformers, many technologies. They are very great. Okay, that's all in this presentation. Anyway, so the important point is that the modern data science technologies utilizes really complicated and large scale, models on the algorithms. That's the point in this page. So anyway, so we are interested in like a very modern data science, which is complicated, large scale. That's all. So and here, so we recently I am particularly interested in like from the statistics to dynamics. So when we are done in the conventional machine learning or statistics, static analysis is really useful, some utility like convex optimization. So the many outputs of the algorithm can be characterized by the some minimizer of the convex function. So it's sufficient very effective to apply the static analysis for the minimizer. And but in this case, everything's like a non-convex and highly complicated as a stochastics. It's kind of like for the neural networks, and the dynamic analysis is more like effective to characterize what to learn and how algorithm behaves. Yeah, that's kind of the simple backgrounds. Okay, so based on these points, so today I try to introduce two analyses, two research project for my team. And the first one is kind of the dynamic analysis on the simultaneously trained neural networks. I will describe the definition later. And then so the second project is kind of the uncertainty evaluation of the high dimensional nonlinear estimation. That's the 2 points. Yeah, this is somewhat overview. So we are statisticians, we are here, so we are interested in the dynamic of the neural networks, and also we are interested in statistical inference of the high dimensional parameters. So, and the first point is that we try to develop the kind of the new dynamical behavior of the neural networks, and then derive some new block dynamics. And second one says that we try to apply some nice results from the physics side, which provides some nice uncertainty evaluation with dynamics, and try to apply these points to the our high dimensional statistical inference problem. Yeah, that's the overview. Okay, so and first I talk about this project on the simultaneous trained neural networks. Okay, look at this point. So yeah, this is the kind of like a joint work with Guillaume Blanc, who is the member of my team in the RIKEN side. And yeah, he's really like a mathematical oriented researcher and delivered a very nice result on this topic. So this is the outline of the first project. Okay, so we are interested in like a simultaneous training of the two-layer neural networks, which means that okay, the neural network have the two layers, and both layers are updated simultaneously. Yeah, it's very simple. It sounds obvious, but it's really hard to like analyze in theory. So that's kind of the background. So and our purpose that okay, we want to show that our neural network can learn nice like complicated functions. And also we try to reveal it's like inner dynamics of the neurons in the neural networks. Yeah, that's our like purpose. And we will show like some like with convergence to the networks and also clarify some dynamics of the neurons. Okay, the background of this topic is the kind of the grand interest of the deep learning theory research field. So the other simple interest is that why neural network like a multi-layer neural networks are like efficient, and in other words, why multi-layers are necessary? That's kind of the grand question of the deep learning theory. So and but the deep networks are really difficult to analyze. So we firstly focus on the two-layer networks. It's kind of the shallow, but the two layers are really essential. So and okay, this is like a two-layer network models. Okay, and X is the input. So W is the weight parameter of the first layer, and A is the weight for the like, second layer. Okay, so W is the first, A is the second, or the two layers. It's really simple, but it's a very complicated in theory. Anyway, so and we are interested in these two-layer neural networks, and the question is why, even though it's a two-layer, but it's nice. Why? It's a question. So and our keywords is feature learning. It's kind of like a near emerging research topic in a deep learning theory. And really roughly speaking, it simply says that the first layer of neural networks learns some kind of the intrinsic structure of data. That's a kind of the rough like overview of the feature learning. Yeah, and so this layer is important. Of course, I mean, in the, for example, like kernel methods of analysis, we do not update the first layer. We only update the second layer in the conventional machine learning or statistics, but in the deep learning, so like we have the two layers. But the first layer is like what first layer learn is essential or critical. That's the keyword, like some insights from the feature learning. Like some nicely updated first layer may learn some kind of like a fundamental, like a basic structure of the data, like a Fourier basis, like some like a fundamental information from data. And then the second layer, they combine have a combination of the to learn structure of the first layer and can like perform a nice prediction or nice interpretation. Yeah, that's kind of the like point of the feature learning. Okay, so this is a kind of high-level message, and several theoretical studies revealed very nice studies try to like give some theoretical background, theoretical validation on the feature learning. So it's very complicated, but there are many nice papers appear in these days. So and okay, that this is kind of some like theoretical example which specify what is the intrinsic structure to be learned and how which program, which network, which algorithm can learn can achieve the feature learning. So that's many nice works. So okay, this is the model and the to be learned, and we know that the W is the first layer and A is the second layer. Okay, and it's also assumed that the data comes from the somewhat the kind of the like a complicated structure. The typical case is the single index model. So X is the input, Y is the output, and Y follows this structure. Like G is a sum unknown nonlinear function, and the Y follows the structure G of some inner product of the unknown parameter times X, which is of course nonlinear in X. And okay, and we do not know G, and we do not know theta here. So, and if we still have the data and we train the neural network from this data, and the nicely trained neural network achieve the result, like the first layer is very close to the unknown parameter theta. So theta represents the kind of the intrinsic structure of the data. So and the nicely trained neural network can achieve the feature learning such that the first layer learn theta. That's the kind of the message, or like a result, what's the result of some nice paper. And also there are kind of the variation of the feature learning is revealed by other data structure like a spiked matrix model and other like a complicated data structure models. So the theory says that owing to the two-layer model, like a first layer can read a nice structure of the data. So and if the first layer learn the kind of the structure of the data, so the trained neural network can enjoy the high performance. And also it's theoretically and experimentally validated. This is some figure from this famous paper. And it shows that, so if we do if we fix the first layer, they cannot achieve the feature learning and the performance is like this. But if we update the feature learning and the first layer learns some integer structure, so the error goes to like this. So this is some gap between the gap between the feature learning and the non-feature learning. So this gap shows the benefits of the feature learning. So in other words, it shows the advantage of the two-layer neural networks. Okay, that's the kind of some of the hot topic in this research field, and also it's reveals the it reveals some of the advantage of the two-layer networks. Okay. But one issue of this theoretical work is that, to achieve the nice theoretical result, we need to design the kind of the artificial set of training. That's kind of the issue we focus, and also other several works focus on. So, to achieve the nice result, we have to simplify the training process, which is necessary to prove the advantage of the feature learning. So some typical cases are layer-based training. Okay, the point is that the definition is that so we start to update the neural networks, but first we fix the second layer and only update the first layer. Yeah, just update here, and after that, so we fix the first layer and update the second layer. Okay, kind of like an artificial setup. So to prove the advantage of the convergence of feature learning, so we need this kind of the training. So in the other there's some variations that we just only the first layer is another version of the artificial training setup. Anyway, so it looks unnatural in the practical sense. Yeah, but it is necessary for theoretical analysis of algorithm. Yeah, because if we update the two layers simultaneously, it's theoretically really complicated, so we cannot do that. So, but in practice, we update both layers simultaneously. So our question is that so can neural networks achieve the similar result on feature learning under the simultaneous training for both layers? Yeah. These questions are raised by also analyzed by this famous paper, like RIKEN, and we try to update their result to the more general setups. So in okay, we describe the our analysis. Okay, so setup is somewhat simple, I believe. So we consider the data distribution, which comes from the XOR function. Okay, so we consider the classification problem, and the XOR function is like this. Okay, input is d-dimensional, but the F star only picks the first two elements and the product, and take its sign, and then also this is the definition of the XOR function. So, and we observe the many data random variables, pairs the x and y. X is the d-dimensional, and y is a binary. So, and it follows, x follows like a d-dimensional Gaussian, and y follows the f star of x. Yeah, that's a kind of a setup. So this is an image, blue dots are data, and on the two-dimensional space, and the red dots are kind of the points for the XOR function. So, and kind of the OTANT can be used to define the distribution of y. So, and next is the distribution data, and we also consider the model which should be updated with the two-layer neural networks, and the script M is a set of neurons. So here we consider many neurons inside the model, and each neuron has a weight, W is which is the d-dimensional parameter for the first layer, and A is a parameter for the second layer, and we take a summation of this network to define the two-layer neural networks. Okay. So, and we define algorithm to update the neural networks, which is here we focus on the simultaneous training. So I think that the definitions are really simple. So we prepared some logistic loss function, and we got some batches, and we define a mini batch loss function, and we define and we for each small t, we define the first we generate the initial distribution of the weights for both layers, and also then we define the updated version of the neural networks by obtaining the parameters, and the obtaining the parameters is defined by this training process. And the W should be like this. It's very simple. Eta is the learning rate, step size, and we take a derivative of each risk and we update the parameters. Yeah, it's very common in practice. So and many practitioners may think that this is a really very practice, and most of all practitioners use this algorithm. But in theory, the simultaneous training is really hard to analyze because so we have to update both layers, and it's highly nonlinear. We cannot use some a nice result from the convex optimization analysis or mean field techniques. Maybe mean field is somewhat possible, but it depends on the strict design of the learning rate. Anyway, so and in the general learning rate, it's really hard to analyze the simultaneous training. That's the one point. That's the motivation. So anyway, but here first I provide some statement. It is not very intuitive, but we just say the final result. So first we define some statement of the learning of the simultaneous training. So here we provide this one. So if the sufficient large training updates, if this this rate, this test data converts to have upper bounded by this term, it's kind of 1 over square root of the log t. It's kind of very slow rate, but anyway, but if t is sufficiently large and the t is sufficiently large, we can see that our loss goes to expected test error goes to 0. So it means that even though you have the simultaneous training, so they can achieve the symptomatically achieve the 0 test error. So it means, in other words, our neural network can learn the XOR function. So its insights are really kind of obvious. We may know that in practice, many two-layer networks can learn the XOR function. But the key, most interesting point is how to prove this one. So to achieve this statement, we need to develop the kind of the new dynamic analysis for the distribution of neurons. Okay, and so in the next from the next page, I will describe how to describe the neurons of the dynamics and how to achieve the result. Okay, that's the kind of the most interesting point in this study. So to show that two-layer networks can learn the XOR function, we developed the two phases of the dynamics. There are two types of the dynamics of the neurons. So each neuron has a parameter W and A, and there are two types of the neurons, individual dynamic and the block dynamic. So individual dynamic is that each neuron evolves individually. There are no interaction between each neuron, between neurons. So we only focus on the it's close to IID of each neuron. So IID is identically distributed. So we only focus on the each neuron. And the second type of the dynamics is block dynamics. So there may appear some clusters or blocks of the neurons, and each cluster takes a typical dynamic. That's the second point. So we define the two types of neuron. So we focus on two phases, phase 1 and phase B. So in the phase 1, kind of the individual dynamics is dominant. Of course, there are several another sub-dynamic, but the dominant dynamics is the individual. So in the phase 2, more block dynamics is getting it's kind of switching. It's then the block dynamic is more dominant in the phase 2. So we describe each dynamic phase by phase and try to show that some kind of rigorous analysis on this one. So the individual dynamic is it's kind of more kind of intuitive. Okay, so simply speaking, each neuron evolves as type process for toward the direction defined by XOR function. That's the kind of the simple explanation. So direction is defined by mu1 and mu plus minus mu1 and mu2. So we know that this is a kind of the plot of the XOR function, and these red points represent kind of the direction, which mainly explains a property of the XOR function. So anyway, so that this green square is like a 4 direction. This is the origin, and this are 4 directions. And yeah, as time, okay, so as the initial phase, the W, or which is the parameter neurons, are distributed as the sphere of the in this two-dimensional plane. But as time passes, like each neuron extract the signal from the direction which is closest to the neuron. Okay, this is like some neuron. This is like a direction in the tangent space. And the kind of the W-seq is kind of the signal part of the neuron along with direction. That's kind of like some definition. So, and the signal is the kind of the main like driver power for the neurons. So as time passes, like each neuron try to evolves to like get along with this neuron by capturing the signal part of each neuron. So and yes, as time passes, like this neuron goes to this way, this neuron goes to this way, and this neuron goes to this way because they're actually more closer to this neuron, and this neuron goes to this way. So that's kind of like some image, like a kind of like some image, and this description is rigorously captured by some mathematics. Yeah. I omit some intermediate lemma's proposition, but yeah, this description is described by some mathematical result. So and after some time, like the neural networks, which is consisted by from the many neurons with individual dynamics, becomes like a signal-heavy networks. It means that the many neurons have evolved along with the direction. So and also the most dynamic of each neuron is described represented by some signals, which means that like a signal-heavy neurons and signal-heavy neural networks. Like yeah, most neurons are very close to this direction, each direction. So and this is the figure, like many neurons here, and the most of neurons are very close to direction. There are some other like several exceptions, but the ratio of the exceptions are not very significant. Significant in this network. So and some lemma says that with some large updates, the only satisfy that the signal neurons are like a norm of the signal part is sufficiently large. And the more neurons are signal heavy as it increases. That's kind of some like a second point. Okay, so and after and also we after we know that we see that okay, neural networks are signal heavy and more and more updates, and finally the neural network converges to this up here converges to some like oracle network. Oracle means that here, which is the neural networks with only 4 neurons with large weights. A large means a large like a large weight. It means that kind of dominant, like a significant only 4 neurons, and which perfectly describe this oracle neural networks. Definitions are like this, and these are some weights, but there are only 4 neurons, 1, 2, and 3, 4, and these 4 neurons is the kind of only 4 neurons are dominant to describe the dynamics of the oracle networks. So, and very simply speaking, some mathematics shows that with sufficiently large T, our train update network is sufficiently close to the oracle network. So an oracle network is described by the only 4 neurons. So it is really very easy to track the dynamics of the oracle network. So we could prove the risk bound, only 4 neurons converge to some point, and these neurons can learn the external function. So and we can derive the final risk bound. So as T increases and also D increases, the test error goes to 0. So that's our how to prove the statement. Okay, so and we put some simple experiments to validate this point. So okay, this is some point if T is small. Okay, so this is a 2-dimensional space, and each some orange and blue points some the width of the neurons. So the T is not so small, but the T is insufficient. Even neurons get close to the origin of the point. But as T increases, the neurons goes to each direction, this direction, this direction, this direction. So and 4 directions. So and as T goes to 30,000, we can show that many neurons get along with this each direction. And it's kind of clusters, and these neurons are very signal heavy. So and we can say that our network can describe by some kind of 4 clusters. We start close to the oracle neural networks. So, and as t increases, we can provide some risk analysis, and after some iterations, we see that the loss goes to zeros, and it is it follows, it's consistent with our theoretical result. Okay, this is a summary of the first result. We integrated Simon training for two-layer networks, and the final result is that our neural network with Simon training can learn extra functions, but in proof, so we describe the kind of the new dynamic behavior of the cluster each neuron or cluster of neurons, and this proof is do not use existing without some existing technique for the complex optimization. So yeah, that's the kind of the result. So there's some insights there's some self-organization of the cluster neuron. That's kind of the insight. Okay. It's okay. We're going to the second topic. It's a totally different topic. It's no neural network. It's more on statistics. And so this is the second point. So we try to apply some physics or dynamical system to another problem of the statistical on the data science issue. Okay, second one is uncertainty evaluation of the high-dimensional linear estimation. And this is a joint work with Sawaya-san, who is a student on my team, and also Uematsu sensei from Tsukuba University. Okay, topic this is a statistical problem for the single index model with high dimensional parameters. It's kind of a totally different topic. So and here the parameters on the sample type is infinity with some constraint. So and our purpose that we try to estimate some unknown nonlinear function of the single index model, and also try to develop statistical inference of the parameters, and we will present some nice result. Okay, the background is that here we are interested in the uncertainty evaluation or quantification of the high dimensional estimation here. So the uncertainty evaluation, which is also known as statistical inference, is a kind of has been a very classical setup, classical interest for data science. So here, this is the data in the data points, and the theta star is the p-dimensional unknown parameters. For example, loss minimizer of the convex loss function. So theta hat is some estimator, kind of for example, empirical risk minimizer, or a maximum likelihood estimator, is kind of the classical estimator. So our interest is that the first interest is whether theta hat is sufficiently close to theta star, which is kind of a common interest. And also additional interest is what is the distribution of theta hat, which is kind of this is kind of the uncertainty of the theta hat. So if theta has a large variance, it's very unstable estimation. But if the theta hat is already kind of more small variance, the theta hat is more confident. So and we have to study the distribution of the theta. That's kind of the classical question. So there's some very introductory, a simple example of the why we are interested in the uncertainty of estimators. The example is a linear regression. Okay, this is the Turing model. So theta star is a true function, true parameter, and the data distribution x and y is characterized by theta star. This is kind of the model. So, but we do not know the theta star. So, but we only observe the finite observation like this. So, and we want to estimate theta star by some conventional estimator, like a least square estimator or maximum likelihood estimator, and also anyway. So, and one of the most common estimator is a least estimator defined by this form, which may appear in the undergrad statistical course. So, okay, but the key difficulty is that because data are random variable, so theta hat is also a random variable. Yeah, it's very obvious. So and to evaluate the confidence of the theta hat, we want to know the distribution of the theta hat, which is a random variable. However, only we observe is just one realization of the theta hat with given datasets. Yeah, because we only have one dataset, so we do not know the theta hat, the distribution of the theta hat. Only we can observe just one realization. This is the data. So there exists some distribution of the theta hat, but this is still unknown, even though we know the theta hat realization is theta hat. This is the one realization, but we do not know the whether the theta hat is kind of the confident. So if theta hat has a large distribution with a large variance, like theta hat can be like less confident. So and we have to evaluate this like a variance or some distribution. And if we know the distribution of the theta hat, so we can enjoy the like some the testing, like derive the p-value also, and we can derive the confidence interval. So then we can like quantify the uncertainty of the estimators. So, and that is a very classical like issue. And it's a very low dimensional case. The really like I mean like some very common approach is like Gaussian approximation, like central limit theorem (CLT). Technically speaking, it is known as the asymptotic normality in statistics. Anyway, so like if the finite dimensional case, low dimensional case, like we can apply the extension of the central limit theorem. So we can say that the distribution of this estimation error has converged to the Gaussian, approximated by the Gaussian distribution. So it is a very valid, it's commonly used, it frequently appears in the many application statistics. But in the high pressure cases, it's like I mean the classical CLT is no longer valid. Yeah, because if this approximation is very sensitive to the dimension. So p diverges to infinity, so nothing is like can be guaranteed. So and we have to develop the new technique. So this is kind of like a very fancy illustration or to describe the difficulty of the statistical inference in the high dimension. So and if the parameter space is a low dimensional, like a low like with a one-dimensional, two-dimensional. So this is like a kind of the Gaussian approximated distribution of the estimator, and which may be close to the theta star, this kind of the image. But if the dimension of the parameter space diverges to infinity, so it means that parameter space are really very like large. So infinite direction to be evaluated. So the distribution of the theta hat is no longer tractable. So in that sense, we cannot enjoy the classical Gaussian approximation in this sense. So we need some more like another rigorous specification of the distribution of the the theta star, theta hat. Yeah, that's the difficulties. So, and here, then we not we, but some like a really nice study applies have developed a new approach to derive the distribution of the estimator. Here, so we focus on some approximate message passing algorithm, which comes from the statistical physics or information theory. So and which define kind of the like a dynamic recursive sequence of the parameters like this. So t is kind of the sequence, and theta t plus 1 with some nice initialization. The sequence of the theta t is defined by the recursive formula. So and this is the kind of updates, and the gamma is kind of the some auxiliary variable, and this kind of the like some special correction term, and it's basically useful in the data science. So, and here the image is like this. So this is the high dimensional parameter space. This is the kind of target estimation. And by updating, by using these dynamical systems, we can generate some sequence of parameters like this, okay. And but the key point is that this algorithm is not only for generate the sequence of the parameters, but key important point is that there exists a really nice theorem known as the master theorem of the approximate passing, and which characterize the distribution of the parameter for each finite t. That's the kind of the really nice result. So as for each t, so and as and p diverges to infinity with some coefficient like with some ratio. So the distribution of the theta t is approximated by some Gaussian whose covariance is like this. Yeah, that's kind of the sorry, maybe and means also specify some sequence, but anyway, sorry, I just missed the type here. Anyway, so we know we can specify the distribution of the theta t. So and it means that even though parameter spaces are very large, but we can specify distribution. That's kind of the intuitive explanation of this result. So and this result may appear in the like this not very famous paper, and recently there's some like some review paper on this topic. So and some like a recent nice paper from Harvard shows that not Harvard, Stanford maybe, and showed that this framework like a high dimensional inference using the approximate message passing. So and overview is like this. Okay, we start with some like a conventional estimator for statistics, like a maximum likely estimator or risk estimator. So and firstly, it is possible to like define the AMP algorithm, which is asymptotically equivalent to this estimator. Yeah, that's kind of the some like a derivation. It is also the ANB is regarded used as like proof device. So and okay, so and we by using the master theorem for NP, we can derive a nice like equation, like a representation of the distribution limit. So and the solution of the equation can be very useful to correct the kind of the bias of the estimator, and also it's very easy, it's possible to specify the distribution of the estimator. Sorry, I have type here. This is the theta. Okay, there's a type here. I'm sorry for that. Anyway, so this is kind of the really like a nice result. So even though we have the infinite dimensional case, but as long as we solve this corresponding equation, we can enjoy the the distribution approximation of the estimated theta hat. That's the kind of the nice result. So and this are used for the logistic regression. So in our interest that we try to like it's very nice framework. So we try to apply this approach to the more complicated models like single index models. Okay, so we focus on this point. So single index model is a kind of the classical model in statistics, but also useful in many machine learning, also related to data science. Anyway, so the P is the dimension of the parameter data. So we suppose we observe the observation of the which is the many pairs of the x and y. X is the P dimensional and y is the scalar. So and we consider proportional high dimensional regime like n and p diverge to infinity with some like a ratio. So and we define the single index model like kind of the distribution of y is described by the g star of x transpose beta star. So and beta star is a kind of true parameter to be estimated, and also g star is an unknown nonlinear function. It should be monotone. Anyway, so this kind of so there's a two unknown elements like a parameter and a nonlinear function. So and also we ask the x is a Gaussian. So and we with some reasonable scale. So single index model can be regarded as kind of the like somewhat more slightly complicated, more complicated model than linear models and toward the deep networks. Okay, so linear models are kind of the, like one of the most simplest, simplest model, and generalized linear model is kind of the extension. And we try to extend the GLM to the single index model with unknown link function, so which can be like more closer to deep neural networks. This is more complicated, but this is like somewhat complicated, also very difficult to analyze. So and there are many studies to study this model, but anyway, I skip the details. So and I present our method, but time is maybe only a few minutes, and I skipped some details, but I provide some explanation of our approach. So the goal is that okay, we're going to estimate the beta hat of for the single index model parameters, and try to show the kind of the asymptotic normality, like a distribution approximation of the like a beta distribution of beta hat. Yeah, that's the kind of the goal. And also we want to estimate the link function step to star. So in our process of the 3 steps, we first estimate the index part by a pilot estimator. We reduce the noise by deconvolution estimator, and we try to apply the high dimensional inference scheme for us in the last phase, last step. So and here, we applied some this paper with the result by this paper, and we tried to this value non-rehearsal index, not with hat itself, but the first we estimated scalar value, which is known as the index part. So and first we derived some pilot estimated beta tilde by some which works without analysis of the D star, and we derived some correction terms, and this comes from the near framework to this framework, but we just we kind of another equation, and we derive some correction term, and we define the index estimator. So which known as it can be a nice estimator such that we see close to some this value plus some Gaussian noise. So and second, we try to estimate the link function G by deconvolution technique. Okay, so we know that the nice index with noise. Yeah, noise is coming at the critical. So we try to reduce the effects of noise by using the deconvolution. So there's some deconvolution is kind of the inverse of the convolution, in the classical sense. So not the CNN. First we transform the data distribution by Fourier to the frequency domain by Fourier transform. So and we divide the Fourier transform distribution by some another calculated function of the distribution. So this kind of derive reducing the external noise. And then we try the inverse Fourier transformation, and we try to recover the original X. That's kind of the kind of the application of the classical Fourier analysis. So and that is effective because that our index estimator is a kind of noise contaminated index. So and we try to reduce this noise. So and here, which is kind of is goes to some statistical model error invariable models, and we try to reduce the contaminated noise by the deconvolution estimator. So and we try by using this point, we can estimate that this unknown function here, like a g here. So by using the estimator, we can enjoy that our estimator is sufficiently close to G star as long as the sample size diverges to infinity. Yeah, that's the one first result. So and then okay, so and okay, I skipped the several details, but after that, so we know that we can estimate the G star here, the unknown linear function. So and we can apply the statistical inference scheme for the high dimensional setups. So yeah, anyway, so finally, so we can achieve the this distribution approximation, with some using the correction terms from the high dimensional scheme from the dynamic analysis. So we can approximate the distribution of the estimated cell. Yeah, this is kind of the valid estimation. So we can develop a confidence interval or a p-value, and this kind of which we developed some a nice new scheme for the statistical testing in the high dimensional setup. So okay, so this is experiments. I skipped the detail okay, G stars are nicely estimated. So and our distribution approximation is consistent with the experiments. Okay, that's fine. Okay, this is a summary. So we are interested in a high dimensional single index model. So and then yeah, I mean, we try to apply the kind of the inference scheme for the high dimensional setup, but using the approximation passing or other dynamical algorithm from the quantum physics. And we try to estimate the link function and the parameter inference, and we developed a nice statistical inference scheme for the high dimensional parameters. Okay, nice result. Okay, so this is my last page. Yeah, so there are kind of the two research fields, and I'm from here, but these fields are really interesting and useful. So I try to bridge the gap between two fields, and then try to establish a new theory. Okay, that's all for my talk. Thank you for listening.